Module in our series on petroleum production engineering. In this module, we shall learn how oil is produced from a well by gas lift, one of the important methods of artificial lift. Our objective shall be to discuss gas lift applications in general, point out the different types of gas lift installations, illustrate the various pieces of surface and subsurface equipment needed for a gas lift system, and finally, we shall show you how to design gas lift installations. But first, let's visit briefly with IHRDC's President Dave Donahue out in California.
Believe it or not, a good example of a gas lift installation is located in that building behind us here in downtown Los Angeles. We shall be visiting it soon, but let's first see how gas lift fits into the life of a producing well.
We have already considered the life of a flowing well and learned to calculate the pressure and flow rate relationships that exist throughout the flowing well system. We found that as the average reservoir pressure decreases, so does the flowing production rate. We also found that at some point in the life of most wells, flow to the surface stops. At that point, or even earlier, the well may be placed on artificial lift, using either gas lift, the topic of this module, or one of several possible pumping systems, the topic of Module 6. The purpose of any artificial lift system, including gas lift, is to reduce the bottom hole pressure in order to allow the well to flow under the existing formation pressure. With gas lift, this can be accomplished by forcing gas through a choker valve located at the surface, down the annulus, through valves in the tubing. The injected gas is allowed to aerate the liquid column in the tubing. The aeration reduces the bottom hole pressure caused by the weight of the column of liquid in the tubing. With sufficient aeration, the bottom hole pressure may be reduced to a point where the well once again begins to flow. The continuous aeration of the fluid column in the tubing will cause more oil to flow from the formation into the wellbore and then to the surface. Over time, though, as more fluids are produced, the average reservoir pressure decreases, requiring increasing amounts of aeration to maintain a constant production level. The lifting of fluids can be accomplished by either continuous or intermittent gas injection. In continuous flow gas lift, a continuous volume of high-pressure gas is introduced into the annulus and tubing at a fixed rate, causing a continuous flow of fluids from the well. This artificial lift method is usually applied to high productivity index wells, which have high bottom hole pressures relative to their depths. For normal tubing strings, it is possible to lift from 200 to 20,000 barrels per day. If we choose instead to inject gas down the tubing and produce the fluid up the annulus, it is possible to lift up to 80,000 barrels per day using continuous gas lift. When small macaroni tubing strings are used, it is possible to obtain production rates as low as 25 barrels per day using continuous lift. The range of continuous gas lift, then, is anywhere from 25 to 80,000 barrels per day. The other gas lift method involves intermittent rather than continuous injection of lift gas. It is generally applied only when a limited amount of fluid is flowing from the reservoir into the wellbore.
Under these conditions, it becomes necessary to wait until the fluid volume in the wellbore builds up to a level worth lifting. Once the fluid builds up to a high enough level, a slug of gas is injected down the annulus through a gas lift valve into the tubing, thereby pushing the column of fluid to the surface as a slug.
Cycling is regulated to coincide with the buildup of the fluid level in the wellbore. Intermittent injection, and therefore intermittent production, is accomplished by the use of a time cycle controller, or an adjustable choke, located at the surface on the gas injection line. Intermittent flow gas lift is ideally suited for a well which has a high productivity index, but a low average reservoir pressure. Or alternatively, a well with a low productivity index, but high reservoir pressure. The major advantage of gas lift as an artificial lift mechanism is the fact that the specific gravity of gas is so much less than that of oil or salt water. The following example illustrates this statement.
Assume that we have 3 6,000-foot wells, each completed with tubing on a packer, and each having a surface pressure of 100 psi. The first well is filled with salt water, the second with oil, and the third with gas. Our objective is to calculate the bottom hole pressure of each. Let's begin with the well filled with salt water. The specific gravity of salt water is 1.07, which is equivalent to a hydrostatic gradient of 0.465 psi per foot. The static bottom hole pressure for this well, then, will be 100 plus 0.465 times the 6,000 feet, or 2,890 psi. Now let's turn to the oil well. If the column is filled with 0.8 specific gravity oil, with a pressure gradient of 0.346 psi per foot, then the static bottom hole pressure will be 2,176 psi. This is more than 700 pounds less than that for the well filled with salt water. Now we turn to the gas-filled well. We are told that it has an average specific gravity relative to water of 0.16, which gives an equivalent pressure gradient of 0.069 psi per foot. This gives a static bottom hole pressure of 514 psi. This is much lower than those for oil and water. The pressure profiles for the conditions obtained in each well are shown graphically here. We see the very low bottom hole pressure that exists when a well is filled with gas.
We conclude from this that if we have a well filled with oil or water and can saturate all or a portion of the liquid column with gas, the bottom hole pressure will be reduced significantly. With a reduced bottom hole pressure, fluid inflow from the formation will be increased and perhaps become continuous. It is the design engineer's job to select the gas volumes, points of injection, and frequency of injection so as to optimize the production from the well. We shall see how this is done later on in this module. Let's take a few minutes now to be sure that you understand the fundamentals of gas lift. Work exercises 5.1 and 5.2 in your workbook. Now, before discussing the design of gas lift systems, let's develop an understanding of gas lift valves.
A gas lift system requires a source of gas and sufficient pressure to inject it at the proper place and rate into our flow system. The injected gas may come from production operations or an outside source of supply. Often, sufficient supply and pressure is available from the high-pressure separator. If the available operating pressure is not high enough, then a compressor will be needed. Prior to injection, the gas typically passes through a flow control choke, which controls the injection rate. Gas lift valves located in the tubing are sized and spaced according to the overall design. The method of operation and type of installation depend largely on the type of valves used.
As you might expect, there are different types of gas lift valves. For simplicity, we shall discuss three types: the casing pressure operated valve, the fluid operated valve, and the throttling valve. Later we shall discuss a fourth type called the pilot operated valve. They're distinguished by their sensitivity to the casing pressures and tubing pressures needed to open and close them. The gas lift industry categorizes gas lift valves according to which pressure has the greater effect on the opening of the valve. This sensitivity is determined by the mechanical design of the valve, because it is the pressure exposed to the largest area in the valve that controls the valve's operation.
We remember that pressure is equal to force divided by area, and therefore that force is equal to pressure multiplied by area. A schematic of a typical gas lift valve installed in a tubing string is shown here. Nitrogen is normally injected into the dome and charged to a specified pressure. The bellows serve as a flexible or responsive element. The movement of the bellows causes the stem to rise and fall, and the ball to open and close over the port. When the port is open, the annulus and tubing are in communication. Because the area of the bellows, A sub B, is much larger than the area of the port, A sub P, it is the casing pressure which controls the operation of this valve. This type of valve, then, is referred to as a casing pressure-operated valve, or more simply, a pressure-operated valve. It requires a buildup in casing pressure to open and a reduction in casing pressure to close.
Let's join Ed DeMoss of Teledyne Merla in Dallas and have him show us a good cutaway of a pressure-operated valve.
We have here a full-scale pressure-charged gasless valve, 1.5-inch size that is wireline retrievable. The various parts of this valve are the dome, the bellows, the packing, upper packing, which separates casing from tubing, the ball or stem, the seat, the back check, and the lower packing. The two packings separate the casing pressure, which enters the valve in this area above the seat, from the tubing pressure, which enters the valve from below the back check, right in this area. Now let's look closely at how the valve works. At the top of the valve, we have a fitting which allows us to apply a nitrogen charge. This nitrogen charge in this dome acts downward on the bellows, which is a flexible membrane. This bellows then will move down or move up as a function of the nitrogen charge and the casing pressure acting on the valve. As the bellows moves, it causes the valve or the stem to move upward away from the seat or to move downward onto the seat. Casing pressure enters the valve above the seat and pushes upward on the inside of the bellows. Tubing pressure is sensed by the valve from this area, and the tubing pressure comes under the seat, and it too acts in an upward direction. These two forces, casing pressure acting upward on the bellows, tubing pressure acting upward on the seat, will open the valve. As the casing pressure then is decreased due to gas flowing from the casing into the tubing, the valve will tend to close and move towards the closed position. The ball will close and touch the seat when the casing pressure has declined to the dome charge pressure.
Now let's take a look at a different type of gasless valve called a fluid-operated valve. Note that the port is exposed to the casing pressure and the bellows is exposed to the tubing pressure. Rather than a single flexible element, we now have both a spring and an optional dome charge supplying the closing force. Most manufacturers of this type of valve charge the dome only when high valve setting pressures require a supplement to the spring force. In this case, because of the large bellows area, it is the tubing pressure rather than the casing pressure which controls the operation of the valve. For this reason, it is called a fluid-operated valve. It requires a decrease in tubing pressure to close.
We have here a full-scale model of a fluid-operated gasless valve. This gasless valve is wireline retrievable and consists of a bellows, a spring, a ball, and a seat, a back check, and the packing, the lower packing and the upper packing, which are used to isolate the casing pressure from the tubing pressure. Let's look at how this gasless valve operates. Going back to the bellows section, in this particular valve, this bellows is never charged with nitrogen. However, some vendors have the capability of adding nitrogen pressure to the bellows in order to operate at higher pressures. In this particular valve, the spring is the only pressure calibration device, and by increasing the load on the spring, we raise the pressure of the valve. By decreasing the load on the spring, the calibration pressure is decreased. As the valve is in the well, tubing pressure flows from the bottom of the valve through these bypass ports and flows all the way up to come in contact with the bellows. This tends to shorten the bellows and tries to take the ball off the seat. At the same time, casing pressure comes through this metal port and moves upward across the check and under the seat, providing an upward force trying to push the ball off the seat. Together, the casing pressure and the tubing pressure will overcome the spring calibration pressure. It's obvious that the tubing pressure flowing through these bypass ports acting on the bellows is the predominant opening force in this valve. As gas flows from the casing through the seat, it turns around and flows into the tubing. This mixture of the gas from the casing into the well fluids inside the tubing will cause the tubing pressure to change. As the tubing pressure decreases to the valve closing pressure of the valve, or the calibration pressure of the valve will then close. The closing feature of this valve is not controlled by the casing pressure, but instead is a function of the tubing pressure.
In the pressure-operated valve, the casing pressure must fall below the dome pressure for the valve to close. It is possible to modify this behavior, that is, to make the closing of the valve somewhat sensitive to tubing pressure if, for example, we use a tapered seat, as shown here. The tapered seat allows the port area to sense the tubing pressure when the valve is open. This means that this type of valve, referred to as a throttling valve, responds to both the tubing and casing pressure even when it is open. If the tubing pressure is less than the casing pressure, it is possible for the throttling valve to close even before the casing pressure has dropped to the dome pressure. In fact, a throttling valve will close with a reduction in tubing pressure even though the casing pressure is held constant.
This type of valve then requires a buildup in tubing or casing pressure to open and a reduction in tubing or casing pressure to close. During continuous gas lift operations, the gas is choked at the surface or controlled by a regulator, so there should be no drop in casing pressure to close the valve. Because the casing pressure is held constant, the valve will open and close then only in response to changes in tubing pressure. Again, we turn to Ed to show us how a throttling valve works.
The valve that we have here is a full-scale 1-inch OD gas lift valve for wireline retrievable installation. Included on this valve is the M latch. This is a throttling type valve and consists of a bellows, a spring, a ball with tapered seat, and in the lower nose is a back check. The packing shown here and here isolates the casing pressure from the tubing pressure. Now let's see how this throttling valve works when it is in the well. Normally the casing pressure is held at a constant value. The casing pressure enters the valve through slots right close to the spring and acts on the bellows. This casing pressure applied to the bellows tends to keep the valve in an open position. The tubing pressure comes in through the bottom of the valve below the lower packing and moves up through the seat against the ball. Now, since this is a throttling valve, there is a measurable pressure drop across the trim, so that this valve senses the actual tubing pressure, and as the tubing pressure moves up or moves down, the ball will tend to move up or move down, and as a result of this movement of the ball, the gas flow rate through the valve will increase with an upward movement or decrease with a downward movement. The tubing pressure is sent from below the lower packing and acts under the seat against the ball. As the tubing pressure increases, an upward force is applied tending to make the valve throttle to a more open position to pass more gas. As the tubing pressure decreases, the ball is allowed to move deeper into the tapered seat, restricting the flow rate through the valve and making the valve pass less gas. This response to changes in tubing pressure allows the valve to be partially open or fully open as a function of the tubing pressure only.
Now let's look at a plot of flow rate versus tubing pressure. It will help us understand the performance characteristics of a throttling valve. The vertical axis is flow rate, and the horizontal axis is tubing pressure. At very low tubing pressure, to the left of point 1, the valve is closed. As the tubing pressure reaches point 1, the valve begins to open and gas flows from the casing to the tubing. The flow rate increases as the port continues to open. Throttling occurs from point 2 to point 3, at which point the port is fully opened and throttling ends. The maximum flow rate occurs at point 4. As the tubing pressure increases from point 4 to point 5, the tubing and casing pressures become balanced and the flow rate drops to 0. During the reverse cycle, as the tubing pressure decreases, the valve opens at point 5. Throttling takes place between points 3 and 2, and the valve throttles close between points 2 and 1.
There are other valves referred to as combination valves, which are also available for gas lift operations. Information on these and other special purpose valves are available from manufacturers. The type of valve to be used for a given installation will depend on whether the well is to be placed on intermittent or continuous lift. If it is not certain which type of gas lift operation will take place, as in cases where a well's performance is borderline, then valves may be selected which are suitable for both continuous and intermittent lift. Valves used for continuous flow must be sensitive to tubing pressure when in the open position. As the tubing pressure decreases, the valve should begin to throttle closed so as to decrease gas throughput. As the tubing pressure increases, the valve should open so as to increase gas throughput. This proportional response to increase and decrease in tubing pressure maintains the established flowing tubing pressure and tends to keep a constant pressure inside the tubing. The ideal valve for continuous flow gas lift, then, is the throttling valve. The types of valves to be used for intermittent lift depend upon whether we are going to install a single-point or multi-point injection system. In single-point intermittent gas lift operation, all of the gas necessary to move the liquid slug to the surface is injected through the operating valve, generally the bottom valve in the string. Let's look at single-point injection on the gas lift simulator at Gulf Oil's New Orleans Training Center.
For this type of installation, the valve should expand to a large port size as soon as it is opened and remain in the fully open position until closing. Depending upon the completion configuration, the port size will range in diameter from 3/8 to 3/4 of an inch. For multi-point intermittent gas lift operation, each valve in turn should allow sufficient gas to pass so as to move the slug to the next higher valve. The pressure under the slug opens the valve it has just passed and supplements the gas being injected through the lower valve. As the slug moves to the surface, the valves normally remain open until the slug is produced at the surface.
Because the opening and closing of the various valves in our gas lift system are so important to its operation, we should take a few minutes to understand how and when a valve will open, when it will close, and what the difference in these two pressures, referred to as spread, really means.
Here we have a casing pressure operated valve. It is a single element valve for which we would like to calculate the opening and closing pressures. To do this, we must write a force balance equation for the valve. The forces trying to hold the valve closed are equal to the bellows pressure, P sub D, times the area of the bellows, A sub D. The forces attempting to open the valve are the casing pressure, P sub C, applied to the area of the bellows, A sub D, minus the area of the stem or port, A sub P, plus the tubing pressure, P sub T, multiplied by the area of the port, A sub P. If we equate these two terms, we obtain an expression for the casing pressure that will just open the valve. It is given here in terms of R, which equals the area of the port, A sub P, divided by the area of the bellows, A sub B. We may apply this relationship to a specific example. We are told that the bellows pressure area is 0.77 square inches, and the area of the port 0.129 square inches. The bellows pressure, P sub D, is set at 500 psi, and the tubing pressure, P sub T, is 425 psi. R is calculated to be 0.167. The casing pressure required to open the valve is calculated to be 515 pounds, that is, 15 pounds above the bellows pressure. A higher casing pressure is required because of the effect of the lower tubing pressure on the port. We may also calculate the closing pressure of the valve once it is opened. Once again, we equate the forces tending to keep the valve open with those tending to close it. We see that the forces tending to close the valve are equal to P sub D times A sub B. The forces tending to hold the valve open are equal to P sub C, the casing pressure applied to the area of the bellows, minus the area of the port, plus the casing pressure multiplied by the area of the port. Equating these two terms, we find that the casing pressure required to close the valve is equal to the bellows pressure or the dome charge. In our example, the bellows pressure is 500 pounds, and so the valve will close at this pressure. The difference between the opening pressure and the closing pressure is 15 psi. We refer to this as the spread. By analyzing our equations, we can show that the spread is a function of the ratio R, the bellows pressure, and the tubing pressure. The relationship is given here.
For given bellows and tubing pressures, we may reduce the spread by reducing the size of the port opening. The spread is particularly important in intermittent gas lift installations because it controls the volume of gas used in each cycle. As the pressure reduction or spread required to close the operating valve increases, the amount of gas injected during the cycle also increases. A small port size, though, increases horsepower requirements, and therefore a balance must be struck between gas conservation and horsepower requirements. The pilot valve was developed in response to the need for a larger port size, while maintaining close control over spread characteristics. It has a small port, which is used for spread control, and a larger port, which is used for more efficient gas passage. The pilot valve, then, answers this twofold need, and is often used for intermittent gas lift operations. Let's go back to Ed as he explains the operation of a pilot valve.
Shown here is a 1.5-inch OD pilot-operated gas lift valve. This is an ideal intermittent gas lift valve because with the pilot, we're able to get complete spread control, very small spread requiring very small ports, but simultaneously with the motor valve section, we're able to always maintain a large port for passing large amounts of gas efficiently. The valve has the familiar upper packing and lower packing, and the casing pressure is always sent between these two packings. The casing pressure right in this area furnishes the large supply of gas which flows to the main inlet valve. Right here under the upper packing are the small ports that supply gas to the pilot. The casing pressure moves through these valves, through these ports, upward, past the spring, and against the bellows. The casing pressure now acting on this bellows seems to cause an upward force overcoming the spring force which is used to calibrate the valve. The valve also senses tubing pressure right here at the very small port of the pilot valve. We're not really concerned that this is a small port because no significant amount of gas needs to pass through the pilot. The pilot is simply a control device. So when the pilot is closed, it controls the main valve in a closed position. But once the pilot is open, it sends an open signal to the main valve. Once the main valve is open, a large 3/4-inch port is made available for efficiently passing large volumes of gas from the casing to the tubing in order to effect efficient intermitting gas lift. Let's look closely at the ports that allow the entry of gas into this main valve. Here we see two ports that provide entry of gas from the casing into the main valve section. Actually, there are four, just exactly like this. The gas flows into this annular area, past the stem, which is down in this headling chamber, around the annular area of the main valve, and then down through the valve and out these exit ports.
We may summarize this section on valves by remembering that a gas lift valve is categorized according to the pressure which has the greater effect on its opening. The casing pressure, or pressure-operated valve, is dominated by the casing pressure both to open and close it. The fluid-operated valve depends on the tubing pressure to open and close it. The throttling valve, or alternatively the continuous flow valve, depends on the casing pressure to open it and the tubing or casing pressure to close it. For continuous flow gas lift, we found that the ideal valve was the throttling valve because it tended to maintain a constant pressure inside the tubing. For intermittent gas lift, we found that any type of gas lift valve may be used, provided it was properly designed. The pilot valve is of special importance because it provides an optimal balance between spread and horsepower requirements. Many valves are spring calibrated, and the dome is charged with nitrogen only when a higher pressure is needed. This allows the valve to operate without being affected by temperature. Some spring calibrated valves are also designed so that the spring load, and therefore the pressure setting, may be adjusted without disassembly. For safety purposes, gas lift valves are usually designed to close in the fail-safe position, and their principal operating components are normally protected against corrosive or abrasive wellbore fluids through the use of special materials. Ed DeMoss demonstrated their method for calibrating a gas lift valve. Let's listen in.
When we get a request from an engineer in a company, he will specify valve trim size and calibration pressure for the valve so that the valve will fit specifically into his well and fit the pressures that he anticipates downhole in his well. Now, with a spring-adjusted valve, as you see here, the desired calibration pressure is obtained by adjustment of this nut against this spring. By tightening the nut tighter against the spring, we have a higher calibration pressure. By loosening the nut away from the spring, we have a lower calibration pressure. Now, an experienced valve mechanic can set this nut pretty close to the desired calibration pressure the first time, but he's only going to get it pretty close. So he makes that adjustment, he assembles the valve, and it looks like this in the assembled, ready-to-test condition. That valve is in the test block. Now, we will close the test block and run a test on this valve to determine its calibration pressure and then to make changes as required. This gauge will be the casing pressure. This gauge over here will be the tubing pressure. Now I'm going to raise the casing pressure on the valve. See the pressure building up, 200, 300, 400, 500. Now I expect a calibration pressure of very close to 850 pounds, something like that. So I'm going to put a little bit of tubing back pressure on this valve. There's about 450 pounds. Then I will continue back up with the casing pressure. 700, 750, 800, 900, 950, 1,000, 1040. The valve opened at 1040 with a tubing pressure over here of about 300 psi. Now watch both of these gauges as I slowly bleed the pressure from the tubing side of the valve. The valve is open. As I bleed pressure from the tubing side, we lose pressure in both the tubing and the casing. Watch how the gauges fall together. Wait, this one's falling faster, so I stop the bleeding. This one has stopped at 840 pounds. That describes or defines the valve calibration pressure. When we have lowered the pressure around the valve at a slow rate, we trap the calibration pressure on the casing side as the valve closes. That is the test block closing pressure or the valve closing pressure. This difference in opening pressure on the casing side as a function of the tubing pressure, remember, 300 pounds on the tubing takes over 1,000 pounds on the casing. 700 pounds on the tubing takes less than 900 pounds on the casing. That difference in opening pressures is a function of the bellows area and the seat area of the ball. And the bellows has the larger area, the seat area is smaller than the bellows. So we can see from this exactly what effect the tubing pressure has in helping to